the organizers very much for inviting somebody who's very distant from the collaboration, but it's been extremely interesting for me so far. And I also have to thank the previous speakers because they essentially gave my introduction and physical motivation. So I'm mainly going to concentrate on some new mathematics, but hopefully you understand why it's relevant and why it's important. And this is based on recent work with a pure mathematician, Ovidiu Costin, who's one of the leading experts in the world in asymptotics and in resurgence. And we've been working on this problem of trying to find optimal methods for extracting physical information from limited information, which I think you'll appreciate is very relevant, not just for theoretical work, but even for experimental work and for modeling and fitting. So I'm going to report some progress using ideas borrowed from Resurgent, and then I'll illustrate with a few examples, one of which overlaps what we heard about already this morning. All right, so I'm not going to tell you a lot about Resurgence, but one thing I can tell you is that it's a deep connection between perturbation theory and non-perturbative physics, and you'll see what I mean by that as we go along. And it's already been known for a very long time that these are related, but the bottom line is that they're related in extremely precise ways that enable you to extract information about one from the other in both directions. So in quantum mechanics and matrix models over the last 10 years or so, this has been established and demonstrated, in some cases proven, but a lot of information, a lot of examples. So at least to me, it's quite well established. But once we move to quantum field theory, things are a lot more complicated and a lot more interesting. And some of the questions underlying this work, motivating this work, is are there ways to relate, say, weak coupling to strong coupling, high temperature to low density to high density, et cetera, relating some parameter where you can get some information to another region in that parameter? And the answer is yes, there are ways, and there are ways of doing it better than we usually do it. So it's worth pausing for a second and thinking where we are in perturbation theory these days, in field theory. So these are heroic calculations that in QED and QCD we know 5-loop orders for many interesting quantities, T-2, beta functions. And these are spectacular calculations, partly analytic, partly numerical, a lot of sophisticated mathematics going into them. But in the last maybe 5 years, there's been dramatic advances that happened just down the road here at Humboldt-Universität in the group of Dirk Kreimer, who was in the mathematics department. They all of a sudden jumped from 5-loop order to 7-loop order in 5/4 theory. So these are spectacular advances using brand new techniques beyond standard perturbation theory techniques. And so they did the full ON dependence of 5/4 and 4D to 7-loop order exactly, 11-loop order approximately, and then they repeated it for phi cubed in 6D with all types of cubic couplings to 5-loop order, jumping from 3-loop order. And this is these combinations of people. And very recently, an idea of Mishi Berinsky is that you can now calculate approximately 18-loop diagrams in 5/4 theory in MS, approximately. And there was a systematic exploration of this up to 13-loop order, including up to 18-loop order by Paul Baldoff, who just defended his PhD thesis last year up the road here. So things are happening, and it begs some questions of what we should do with all this information. So I want to start off by asking to look towards the future. Suppose we have this very high order information about interesting quantum field theories, ones that are really non-trivial, and then take into account the fact that you lattice people are making spectacular progress very rapidly in many interesting directions in terms of expansions and fittings and extrapolations. A lot is happening, and I think it's happening very quickly. As an outsider from the lattice community, I think it's incredibly impressive progress. So the question is, what should you do with all this information? Is there some optimal procedure? Are there better things? And if so, can you quantify how much better they are, what the errors are? And these mathematical questions just haven't been asked until now. And the bottom line is that there are simple things you can do that are much, much better. And I want to convince you of that by a few examples. So you can take the technical problem. Suppose you calculate something to some order, and you're doing a difficult problem, Yang-Mills, QCD, something really difficult. And with a lot of hard work, you can calculate some number, 5, 10 maybe, expansion coefficients. What should you do with that? What does it mean? And is there a best way to mine this? So the first approximation to mining is you dig a hole in the ground and you pick stuff up. A more realistic approximation is you need all sorts of special tricks to dig something out. And at the moment, we're just constructing this mine, working out ways and tricks and special methods. So let me say a little bit about resurgence. I don't expect you all know what this is, but it's a fairly recent development in mathematics that came from studying what are called dynamical systems, nonlinear coupled differential equations. And it's a way of combining perturbatively small things with exponentially small things systematically in a way that's unified. And the great discovery of Écart, who's this pure mathematician in Paris, was that in doing so, you learn that there are all sorts of connections between the perturbatively small things and the exponentially small things. They're related in a very deep and systematic way that you can use to your advantage. And it's even just a matter of thinking in terms of that perspective. It raises all sorts of possibilities and questions that people had just never thought of before. And now if you go back through that lens and look at things, certain things have been discovered now where they could have been discovered 100 years ago if people just asked the right questions. So the message is, and these raindrops here are supposed to represent expansions around certain special points in your problem. Could be infinite temperature, 0 temperature, near a critical point, near some other critical point. And the ripples there are supposed to be these fluctuations. And the message is that in any natural problem, meaning anything we're going to confront in physics, these ripples are related to one another. So the very extreme version of this is that if you know the ripples around one of these points, in principle, you can extract the ripples about all the other points. Okay? And that's been demonstrated explicitly in certain quantum mechanical models and matrix models where there's an infinite number of critical points. All right, so now let's go back to the original question. Let's suppose this is true. It sounds very suspicious. It sounds miraculous. Let's suppose it's true. If it's true, it should mean that we can take advantage of that information to devise ways of extrapolating that are better because we're using more information. Right? So that's the idea. And surprisingly, it actually works. So I think everybody's familiar with the fact that perturbation theory is generically divergent. Not always, but generically it's divergent. We can therefore control it by doing what's called a Borel transform. It's just an inverse Laplace transform. If you don't know what that is, don't worry. It's just some transform that regularizes the problem, and now you can work more systematically, mathematically, and then you transform back again at the end. And physically, in this Borel plane, things become convergent, but because if they have a finite radius of convergence, as Vladdy explained very nicely, because they have a finite radius of convergence, they have singularities somewhere, which are very often in the complex plane. So real physics is very often governed by singularities that are in the complex plane, even though we're doing real physics. Okay, we're familiar with that from optics and quantum mechanics. Shouldn't be any surprise that it happens in field theory also. But then that means that if we're solving a physics problem, these singularities are not just in some random place. Right? If you're a mathematician, you can devise some crazy function or crazy differential equation that has singularities all over the place in weird places. But that won't happen in a physics problem because those singularities are actual non-perturbative objects which interact according to some rules And so in some sensible theory, there will be structure there, and that's what we're looking for, okay? So the idea is, let's see, can we devise better analytic continuation extrapolation methods that is based on the assumption that this structure is there? And either it works or it doesn't. The strategy is that the thing that's really important in doing this precisely and getting extra precision is to understand the local behavior at the singularities. Everything else can be taken care of extremely easily by simple things like Pardé. But to increase your precision, you have to get more information near the singularities. And there are ways to do that, and there are ways to do that that gain you dramatically higher precision. The good news is the basic toolkit is really simple. There's a set of things you can do, you can try, they're recipes, and they're quite easy to implement in practice. So here's a more precise statement of the problem. Suppose you're given some function, some free energy, some correlation function, some spectral function, and you know something about it. The most interesting questions about it are, does it have singularities? And if so, where are they? If they have singularities, what's the exponent? Is it square root? Is it logarithmic? What is it? Is it a pole for some reason? What's the coefficient? What's its strength? Right? It's called a Stokes constant. It could be highly suppressed for some reason. It could have a coefficient that depends on some other parameter, and that strength could disappear as you change that other parameter. So this is an interesting, difficult problem. And can we extrapolate from one Riemann sheet to another in a systematic way? And so those are the background questions I want to have. And so if you're in a problem where you're dealing with an asymptotic series, you go to the Borel plane, and now you're looking for these singular critical points. Or you might be in a problem where it's actually not an asymptotic expansion. You've just got a free energy, and you're just looking for critical points anyway. Okay? All right. So here's a little aperitif. This recent work going in 5/4 theory up to this 7-loop, 11-loop, 18th loop order, you can ask yourself the question, can you already see that this perturbation theory is divergent, factorially divergent? Is that enough information? If you only have 3 terms, you're not going to be able to see it. But if you start having 7 or something, maybe you can see it. And if so, there are 2 possible candidates, physical candidates, for causing this divergence. One would be that it's due to the instanton. This is a Lipatov type argument. And the other would be that it's due to a renormalin. Okay? And since you have the full n dependence, this is the ON symmetry of the 5/4 theory, the instanton would predict this form of the large order growth. I've normalized the instanton action to be 1, whereas renormalins would predict a completely different n dependence of the large order factorial growth. So you can ask a first order question, is it factorially divergent? And then you can ask, if so, can I tell between the 2? And a very, very simple exercise with my student, we just took this information, did some very simple, straightforward ratio tests, and yes, they're consistent with factorial growth already, and you can see that the instanton interpretation is favored for these RG functions. Okay? So this is just a little teaser that now that we start getting something like 7-loop information about these functions, we can start to ask these questions and maybe get some answers. All right, now some little detour and some mathematical background. Unfortunately, divergent series have a bad reputation amongst physicists. They're regarded as problematic. I would argue that they're actually much more interesting. They can contain a lot more information, and when you know something about them, they're actually dramatically more accurate than convergent expansions. So, for example, you will often hear some version of this statement, that it's a waste of time. Okay? You even see it in serious books, and it's absolutely not correct. The thing that is correct is that if you just truncate an asymptotic series at a certain order, and then you try to dial the variable, it will get worse the higher order you go. But you just did the stupidest thing possible with this truncated series. Okay? You just truncated it. There are things you can do that are very simple with that truncated series where the precision gets much higher and, in fact, exponentially higher with the number of terms. And so this exercise, Costin and I did this exercise, that you just take this generic situation in physics where the coefficients increase factorially. This is, there are books filled with examples where this is the behavior. And then you just estimate the error using some fancy orthogonal polynomials techniques. And you see that if you just simply truncate, capital N is the order of truncation, the error grows with n. And you've all seen these pictures where it cuts off closer to the expansion point as n increases. But if you just do something really simple, like take that truncated series and do Padé in it, this is expanding around x equals infinity, you discover that actually now the error decreases with n, and the scaling of n times x means, so this is going from x equals infinity, you'd like to decrease down, extrapolate down near x equals 0. This says that you can roughly scale down to like 1 over n in x. So you can go from x equals infinity with some chosen precision down to 1 over n. If you do something slightly different, namely you first Borel transform and then you do a Padé, then you gain an extra factor of n. And I want to emphasize, it's a totally trivial step. You've just got a number of coefficients, you do Padé, but before doing Padé, you divide by n factorial on the coefficients. It's completely trivial. But you gain 1 over n factor in precision. So if n is 10, that's not so bad. If you do, in addition, before you do Padé, you do a conformal map, then it goes like 1 over n to the 4th. Okay? So just think about it. If n is 5, you just take exactly the same information. You simply do a set of steps that are each, one line in Mathematica, or do it by hand, and a dramatic improvement in precision. And we have all the constants and subleading errors. These are just the leading things. So you can really quantify what's going to happen when you do some of these operations. And we've already seen in many talks people doing conformal maps and whatever, and people seem to do it just because sometimes it works and sometimes it doesn't. But now we know exactly why it's working and how well it works. So, yeah.
But there are things that are simply not seen.
I'll come to that. Okay. Yeah, I don't want to go down the Resurgent line too much. I want to just talk about extrapolation. So let me just summarize the lessons. The main lesson is it really makes a difference how you process this information. And it's not a small effect. It's a huge effect. If it had been a small effect, okay, forget it. It's not worth learning anything new. It's significantly better to work in the Borel plane than in the physical plane. People sort of had evidence of that, but never understood why it was true. If you use something like a conformal map before doing Padé, it's dramatically better again. If you do something called a uniformizing map, which is just some slightly more complicated conformal map, it's even better. And you don't have to know all of the information about all the singularities in some really complicated problem. Even if you just know something about the leading singularity, it's already a dramatic improvement based on that. And the most important lesson is it's actually kind of simple to use. So let me say a few things about Padé, because Padé is another thing that physicists use very often, and it's somewhat mysterious. The problem is if you only have a finite number of terms in a series, then your function or your Borel transform, it's a polynomial. So it has no singularities, right? It's a polynomial, it has roots. So one very powerful, very simple step that gets you some limited information but is worthwhile is you convert this to a ratio of polynomials, that's Padé. It's built into every Mathematica, MATLAB, Maple, blah, blah, blah. There are explicit expressions, determinant-like expressions for the coefficients. It's a very well understood transformation. And you just match the coefficients to the order that you have. It's algorithmic, it's very simple, but since it's a ratio of polynomials, the only possible singularities Pade can produce are poles, obviously. A lot of physical problems have cuts, have branch points and cuts. So how does Pade handle that? Pade will produce an accumulating set of interlaced poles and zeros that accumulate in the limit that n is very large towards a branch point that's a real singularity. That's what Pade does experimentally, and I'll show you in a minute why it does that. Here, there are very few actual solid mathematical results about Pade, but some empirical observations. Diagonal and near-diagonal are the most useful. It's kind of obvious. If you take a polynomial and you take it as a ratio of a polynomial over 1, you don't gain much. And if you do 1 over a polynomial, you also don't gain much. So it's somewhere in the middle that it's going to be most useful. There's a very deep relation to orthogonal polynomials because it's very easy to demonstrate that the two polynomials in the numerator and the denominator, they satisfy the same three-term recursion relation. And anytime something satisfies a three-term recursion relation, it means it's an orthogonal polynomial. That's a simple theorem in linear algebra. But there's only convergence results in very, very special cases, these so-called Riesz-Markov cases, where the function can be written as an integral over a positive measure with these pole-like singularities. Right? It's only in that case that there are any local convergence results. So sometimes that happens in physics, but very rarely. This is a special case. Even some very simple questions and some long-lived conjectures, they've been proven false by simple counterexamples. So things that you would think must be possible is simply not true for Pade. So the problem is it naturally produces spurious poles and things called Faussade doublets. And ultimately, the reason for this was only understood in work by Stahl about, how long ago is that, 25 years ago, that the inherent instability is because if this is not a bona fide Hilbert space positive measure, then all the proofs just fall out the window. Now, it's worth thinking of this like a physicist. What Pade is actually doing, this is very interesting. So, Pade, you just take ratios of polynomials and expand, or you write down determinants. But what it's actually doing is solving a two-dimensional electrostatics problem. Think of all the poles as charges. What Pade actually does is it distributes these charges in such a way that you think of it as a conductor made of a deformable wire, and the ends of the wires are the actual singularities, and you change the shape of the wires connecting these to minimize the capacitance. That's what Pade actually does. And this was only realized in detail something like 25 years ago. Okay? Once you know that, you can think like a physicist. So I'm showing here an example where there are, 4 singularities. So there's a wire here, and Pade just dumps poles wherever, depending on how many terms you have and what precision you have, to try and minimize this capacitance. Now, if you think like a physicist, you say, let me say, suppose I think that maybe there's another singularity somewhere here. You can just artificially put another charge somewhere near that, and the real charges have to be a branch point. So Pade will deform the wires with an extra vertex to see that charge. So you can actually probe this, when you think about it as a physicist, using these electrostatic analogies. All right. Now, we've already seen these conformal maps in several talks. So imagine there's one singularity here, I'll put it at -1 with a branch point. This is the simple conformal map from this p-plane to this zeta plane. You just map this cut plane inside the unit disk. The upper side of the cut becomes this. The lower side of the cut becomes this. If there were another singularity buried in that cut, it would appear on the unit circle somewhere, in this case here. So this is featured already in maybe 5 talks in this conference. And the reason is just that you've identified the fact that there's a leading singularity, a threshold, and you've just changed variable to the right variable to describe that situation. You've ignored all of the higher singularities, but just based on the information that there is a threshold, you can dramatically improve whatever you do, fitting, resumming, whatever. And that's why it works. Now here's an example. Just take some simple function with a branch point at -1 and the 1/3 exponent. So here's a plot of the imaginary part of the actual function. There's a cut starting at -1 off to -infinity. If you ask Pade with 10 terms, it gives you 5 poles and 5 zeros. And it's extremely accurate away from the cut, but it's absolutely terrible near the cut because it's put poles there trying to pretend that it's a cut. Okay? So when you go out here, Pade is very good. Near the singularity, which is the most interesting place, and that's the place where you get extra precision, Pade is terrible. This is if you just do a conformal map and not Pade. It's better, but it's still got this bad structure near the singularity. This is if you do a conformal map and then Pade, and you cannot tell the difference from the real function. Same number of same input, just treating one extra step. Right? Dramatic improvement. Very often in applications, and we saw an example in Vlad's talk, you get this interference between different singularities. So what does Pade do? Well, you might think if there are two poles at e to the I pi over 3 and e to the minus I pi over 3, that maybe, these are two branch points rather, you may think that it would put straight line cuts along here. No, that's not the electrostatics problem it's solving because there's a singularity at infinity. So this is actually an example where this is the expansion around 0. I should invert it to an expansion around infinity. There are 3 tips to the wires, so this is a 3-pronged capacitor. And it changes the shape of that to minimize the capacitance with the number of charges it has. These are spectacularly sensitive to getting the right exponent. If you shift a square root exponent by something like 10 to the minus 4, you change from this to this. Okay? So if you can tune somehow the exponent to be a half integer, or a half, then you can identify the exponent with absurd precision once you realize what you're looking for. Now, anybody in this game from the mathematical side, it's almost compulsory that as soon as you propose a new method like this, you have to apply it to their version of the harmonic oscillator, which is called the Penlevet-1 equation. It's the simplest, interesting, non-trivial, nonlinear differential equation, which is this one here. So it's nonlinear, it's y squared. Okay, so this is one of the classic examples. If you propose any method, you are absolutely compelled to say something about this. Otherwise, nobody will listen. So here's what happens. Here's the solution generated at x equals plus infinity. It's very easy to see from scaling that this is the right variable. You just put this ansatz in, and you can generate hundreds, thousands of these coefficients. Totally straightforward. And then you can ask, well, this is a very famous equation. They know that it has 5 different Stokes regions. It crosses these Stokes boundaries with nonlinear Stokes transitions, very intricate, very complicated function. Once it goes into the shaded region, the function looks nothing like this. The function looks like this. It's meromorphic. And it's characterized by some poles that are not quite uniformly distributed in here, but it looks like they're uniform. And the strength by 2 parameters, since it's a second-order equation. So here's a question. Suppose you give me some of these coefficients that are extracted from out here. Do those coefficients know that when I continue in the complex plane across this nonlinear transition, that the function should look completely different in the other region? Right? Surprisingly, mathematicians hadn't asked this question. So this is what happens. If you just take this, apply this conformal and Pade, you take this series in x to the 5/4 and just extrapolate it using those simple steps. And what happens is that extrapolated function completely changes to look exactly like this with 30-digit precision. Yeah. So somehow those coefficients generated in this region knows something about the function in a completely different region where it's gone through very, very complicated transformations. It's amazing. That information is sitting in these coefficients. So this is an example of resurgence. The coefficients generated about some distant point know something about how the function's supposed to behave in a completely different region. And this is a very non-trivial transformation of the sort that we might think of and expect in physics, where we use some degrees of freedom to describe a problem in some regime. In another regime, it's a completely different description. The variables have changed. The structure of the expansions have changed. And somehow that expansion over here knew about what it was supposed to look like over here. All right, so we can do even better than this. There's an optimality theorem. If you use one of these elliptic function maps, it's an exponential increase rather than a power law increase. I won't go into the details, but here's a plot of a function with one branch point, the ratio of the approximate to the exact. This is if you just do Pade, right? We're going very, very close to the critical point, so Pade bombs eventually. You do a conformal map and it's much better. If you do this uniformizing map, you cannot tell the difference all the way up. So you can get within 10 to the minus 40 to this branch point using just some very limited number of terms. It's dramatically better to use these uniformizing maps. I don't think I have a time, well, I have to say this. So imagine imagine you have two cuts like this, and I'll show why in a second. You can have an expansion around the origin on this first sheet, and that information knows about all the other sheets. The question is, how do you cross the branch cuts smoothly from one sheet to the other? And the answer is you use one of these elliptic functions, and they're very simple. You don't have to know much about them because you're only going to use a finite number of terms of the expansions. And you can cross from this sheet across here onto the next sheet just by mapping into this conformal map. Doesn't put you in the disk, it puts you in this blue region. And if you then re-expand here and extrapolate across here, now you're on the second sheet. Now you're on the third sheet. You can just keep going forever, in principle, if you have enough information. And I was going to show an interactive file, but it's not going to work here. Now we can apply this to a physics. So fortunately, Vladi explained this is this Ginzburg-Landau argument where, in the end, you're trying to solve a cubic equation. Once you've done all this rescaling that Vladi mentioned, you're trying to solve a cubic. So you know there are 3 sheets. But because of asymmetry, you know that there are basically only 2 sheets. There's one sheet, so complex conjugate of the other. And physically, in these problems, this is a high temperature sheet and this is a low temperature sheet. So if you have some terms of an expansion here, and you want to explore the first sheet, well, you do something like Pade, and it's very good, but it's hopeless when you go near the cuts, for the reasons I explained before. So how are you going to extrapolate across a cut if your representation is terrible near the cut? Right? You obviously can't do Pade or even. So amazingly, if you do this uniformizing map, and you just, so this is in this generic Ginzburg-Landau type argument, just if you use a truncated series, it bombs near the radius of convergence set by these Li-Yang guys. If you use Pade, you get this dash thing. And if you just use half the number of terms, the uniformizing map it's essentially perfect. It's very far away. But you can even go to the next sheet. So as I mentioned, to get onto the low temperature sheet, you just do exactly the same map into this region, re-expand with Pade, and you can now just go wherever you want. You can wander onto any sheet, and it crosses smoothly across this cut, absolutely no obstacle, and you can generate these nice behaviors here through these critical points, and you essentially can't tell the difference between the exact answers and this uniformized one. And this is the only method I know of that can smoothly go across a cut, and you can do it with just 10 terms of the expansion on one sheet. It's almost laughable how little information you need to go across a cut, and there's no other method that will do it. All right, how am I going now? Do I have maybe 5 minutes? 5 minutes more. Okay, so since Vladi made a very good case for this being, an interesting generic structure of a critical points, set of critical points for not just one problem, but for a whole universality class of problems, you can study the same sort of thing with other universality classes, say if you include a phi to the 6th term or something like that, and it's the same feature. If there are a dominant number of branch points that are small, you can do all of these uniformizing maps and conformal maps explicitly. And it's extremely simple to implement, and so why not do it? One last example is I want to make a comment about the derivative expansion, because that was also mentioned in Vladi's talk, is that if you're familiar with this famous old calculation by Heisenberg, 1935, he did not only the first field theory calculation, he did the first non-perturbative field theory calculation with his student Euler. They calculated the one-loop QED effective action in a constant electromagnetic background field. They defined renormalization, charge renormalization, the defined effective field theory. If you read Euler's thesis, it reads like a modern textbook on effective field theory. It's really impressive. The reason they could do that was because the determinant in a constant background field is soluble, nevertheless. So now this is of interest in many gauge theory problems, but you want to go beyond constant field, and you want to study intense fields, very strong fields from weak fields, and you might want to go from a magnetic field to an electric field, which is like a Minkowski to Euclidean analytic continuation. And so you can ask a very primitive question. Suppose here's the exact representation in a magnetic field. Here's the weak field expansion. Here's the strong field expansion. But suppose you just give me a few terms of the weak field expansion. And ask, from that, can you learn how it behaves at strong field? And can you learn how it behaves in an electric field, not a magnetic field, which is an analytic continuation like going from imaginary chemical potential to real chemical potential? And the answer is you only need about 10 terms in that expansion, and you can extrapolate from weak field to strong field through 7 or 8 orders of magnitude, and you can get the exponentially suppressed imaginary part across, 4 orders of magnitude from 10 terms of the weak field expansion. Okay? So these are very dramatic extrapolations. If you just think about it in these terms, it's an extremely simple calculation. You can even do it at 2-loop where there is no known simple expression like the top line here. And I stress that this number here, this coefficient of the log, that's the 1-loop beta function. That 1/3, the coefficient of the log behavior is the beta function by definition. And the point is you can extract that 1/3 from 10 terms of the weak field expansion. Numerically, approximately, but you learn that it's roughly 1/3. That information is buried in the weak field expansion. You can then generalize this to an inhomogeneous field, and this is important in astrophysics, in plasma physics, and in upcoming laser particle physics experiments, where people use very, very intense lasers. They're very inhomogeneous because they're very intense, and yet all of the simulation codes are built on what's called the locally constant field approximation, which is the leading derivative expansion. And it's well known that that's not good, but nobody had a better idea. And so we applied this Resurgent extrapolation not just to the weak field expansion, but in the inhomogeneous cases. And it's just dramatically better. So the blue line is the exact result. This is the locally constant field approximation. This is WKB. When the field is very inhomogeneous, both of those approximations are hopeless. You use these extrapolations, and you can't tell the difference from the answer. Okay, I think this was with 15 input terms. You can do the same thing for the electric field. So now you're looking for signals that are exponentially small, and you can still do the extrapolation with very high precision. And again, these other approximations that are widely used are absolutely hopeless. So we're proposing this as a different way of looking at extrapolations. So I'm going to have to stop now, I think. So let me just stop. So you can read that.